So when last year sometime I told David Merman that I was thinking about Wigner's friend, well, his reaction was this. Funny, I would have thought that Wigner's friend was the quantum paradox that QBism disposes of more readily and unambiguously than just about any other. And that's true. But still, the recent versions of Wigner's friend that, I mean, it's quite a long list now. First Časlav and Daniela Rudiger and Renato Renner and others came up with. Actually, they were fruitful in forcing us to think more carefully about some things. So QBism has addressed Wigner's friend before. Chris already mentioned the 2007 paper where we introduced the phrase facts for the agent, although he also mentioned, and I should really acknowledge that, all the credit goes to him because he put it in against, for instance, my resistance. And secondly, then I think the full QBist account of Wigner's friend was worked out in Chris's 2010 paper. So a very brief overview of QBism, 4 tenets, probabilities, all of them, including 0 or 1, are valuations that an agent ascribes to his or her degrees of belief in possible outcomes. So these are numbers you use to bet or gamble on the outcomes of experiments you perform. The Born rule is normative, not descriptive or prescriptive. Quantum measurement outcomes are personal consequences for the agent gambling on them, and the measurement apparatus is conceptually an extension of the agent. And I think this falls outside even the Copenhagenish interpretations that Matt was just describing.
Can you say why?
Well, one reason, for instance, is here.
Sorry, which you're going to say more about that, though.
Yeah. I'm going to say more about
that. Oh, okay. Because I doubt anyone in the audience knows what the hell normative.
What about descriptive? I mean, when we have you talked a lot about describing systems, and we are not doing that. But okay, I mean, but this is not about. I mean, basically, this is not a reaction to your talk. So, so here's another quote. When Daniela and Renato published a paper in Nature Physics, Matt Pusey wrote the commentary, and it was this sentence: "What felt to me, at least, like squeamishness about recognizing what seemed like unproblematically objective facts appears now to be crucial to QBism's consistency." So that refers to QBism's insistence that measurement outcomes are facts for the agent. So that's not the only QBist choice that has led to puzzlement in the past and still leads to puzzlement. So here are some. So first is what Matt referred to. Why the insistence that measurement outcomes are personal to the agent, but the other things. Why on earth does QBism insist on belief rather than knowledge? Quantum states of belief rather than states of knowledge. Why does QBism insist that unperformed experiments have no results even in the case of probability 1? Why the insistence that physical systems are not constrained by laws? And why the insistence on SEECs, symmetric informationally complete measurements? So all questions people have asked and should puzzlement about. Okay, so let me just very briefly go over belief versus knowledge. Knowledge suggests knowledge about a system's real properties. I mean, of course, you could use knowledge in a different way, but this is really what is suggested very often, and it led using knowledge instead of knowledge for a quantum system led to a lot of misunderstandings. So, if knowledge suggests a system has real properties, well, you're very quickly in the framework of ontological models, which Harrigan and Speckens defined like this: for any measurement on a physical system, the outcome probabilities are determined by the system's real properties, and let's call them lambda. So, and in such so if you had a psi-epistemic ontological model, then psi would be epistemic, but would express knowledge about these lambdas. And then, of course, no-go theorems, as probably everybody knows, they start to bite, and you have, I mean, most famously PBR, Pusey, Barrett, and Rudolph. Assuming lambda plus some further assumptions implies that psi is determined by lambda. In QBism, probabilities are not determined by real properties, and psi wave functions, quantum states, encode an agent's degrees of belief about potential measurement outcomes. It's not knowledge about properties, but belief about potential outcomes. Next one, probability 1 beliefs are beliefs. Here's an example from horse racing. Let's see, for some reasons I'm certain that Albatross is going to win the race. So I write down that P of Albatross wins is equal to 1. Well, all that means is that I'm willing to pay any price less than $100 for a ticket that pays $100 if Albatross wins. So in a strictly decision theoretic, Bayesian, Definetti-ish approach to probability, this is the meaning of this statement here. And it does not mean that there's an objective feature of the world, that there's some lambda that guarantees that Albatross will win. And so we take this seriously and therefore reject the EPR criterion of reality. And just to remind you of it, if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So that's precisely, if you can predict something with probability 1, then there must be a lambda that makes it true, which is precisely, again, what QBism does not assume or reject. Okay, so, and that's crucial because it blocks the move of deriving lambda from perfect correlations in a Bell scenario, for instance. Okay, so here's the list of QBist choices led to puzzlement. Now you might view them as just a list of ad hoc things you just invent in order to get rid of certain problems. Well, that's not the case. They all flow from the way QBism views the Born rule in the formalism. So here's the Born rule. It is an addition to probability theory. It's a normative consistency requirement that agents should adopt when gambling on the consequences of their actions on some part of the world external to themselves. So the idea, I mean, when I say gambling, well, people sometimes say this is frivolous talk about gambling. It's really is decision making, but gambling is the purest and simplest form of decision making. It's idealized, of course, but then I mean, decision theory is always idealized. Probabilities are always idealized. So it's about decision making. It's about gambling on the consequences for yourself of actions that you take on the world, and is the world external to yourself. And it's just a consistency requirement. So this has all these consequences. I mean, just first let's make this a little more concrete. So the Born rule actually connects probabilities. It's a consistency requirement between different probability assignments. And so the way to set this up, I mean, the standard sort of quantum scenario is that you have a system, you describe it by a quantum state, and then you perform a measurement on the system. And in most general cases, measurement is a pure VM with outcomes Q of J, and J labels the possible outcomes.
With probabilities Q of J. You said outcomes Q of J.
I meant probabilities Q of J, and J labels the outcomes. Thank you. And now the Born rule. So rho is the quantum state here. EJ are the PRVM elements that characterize the measurement apparatus, and the Born rule has the standard form here. And now there is a nice way of turning this just into a statement about probabilities. And that's by introducing a reference measurement, a fiducial reference measurement here. So this is where the seek comes in. So this I mean, basically in the most general case, there should be a fiducial measurement which is informationally complete. That means that the state of the system is determined by the probabilities P of I. So that's what informationally complete means. It means that the outcome probabilities determine the quantum state. So therefore now by specifying rho, basically all I'm specifying is my beliefs about the outcomes if I were to perform this particular measurement on that system. Now I can use this fiducial measurement also to characterize my measurement down here, the PRVM elements. And that can simply be done by looking at the conditional probabilities to get outcome J here, conditioned on having got outcome I here. So this is a stochastic matrix R of J given I, and that completely characterizes any PRVM, any measurement down here. So now I've basically turned these objects rho and E or rho and EJ into probability distributions. I can rewrite the Born rule in terms of them. Q of J is just some function of these probabilities, and so you see the Born rule now is simply a way of connecting these probability assignments. Okay, so now I mean this idea that the Born rule is just a consistency between the probabilistic beliefs of an agent that is so central to QBism that I mean, you would like to make the Born rule in this form the centerpiece of your formalism, and I mean this is a simple and pleasing formula here. For most informationally complete measurements you could insert here, this is going to be a horrible mess. But if you turn this, if you use a symmetric information complete measurement is seek here, you actually get a very simple, very suggestive formula for the Born rule. So this is the Born rule here, and you see it actually looks very much like the law of total probability. If you get rid of these d and d plus 1 factors here, but in order to turn the law of total probability into the Born rule, you just adjust by these dimension-dependent factors here. Okay, so what are consequences of making the Born rule, giving it this particular role in the formalism? What are the consequences? Well, the first one is there is no quantum state of a system unless a system is an agent assigns one. The quantum state is an expression of my belief about measurements I could perform on the system. So if I have no belief, if I haven't thought about the system, systems don't have quantum states. I assign quantum states to them if I want to do experiments on them or draw conclusions from them. So systems don't have quantum states. I assign them, and in particular, before 1925, there were no quantum states in the world.
1926.
This is similar to this idea of facts for the agent.
Schrodinger wrote down the first wave function. 1926.
I stick with before 1925 there were no wave functions. It's a true statement. Assigning a rho to a system is a big commitment. It's not just, I mean, you just write down this is my quantum state. You actually, it is equivalent to making gambling commitments for arbitrary measurement on the system. So this is actually, I mean, you are expressing very sort of detailed beliefs about a system. So it's not something you just write down. It's an important step to do that, and it's difficult. It's a big commitment. It's not Q of J are prescribed by the given rho and E. This looks like that rho and EJ are sort of given, and then this fixes my Q of J's. This is just one particular way in which one might use this, but in general, it is really a consistency requirement. So we say the agent must strive to assign probabilities to all these measurements and the conditional measurements so that the Born rule is satisfied. That's a normative struggle, and usually this is actually very difficult to achieve that, and is not something that's handed to you on a platter. And finally, is it finally? Maybe not. The Born rule is just about my gambling commitments. So therefore, and the Born rule implies the quantum formalism. So the therefore does not put any constraints on how a physical system behaves. So it does not, the quantum formalism therefore is not a law or does not provide any laws that tell a system what to do. So in that sense, we say there are no laws. Okay? Now this is, I mean, this can be dramatized with this nice quote here.
Just to slow you down, sorry.
Slow me down.
Yes. So Adán Cabello likes to say, if you go back to the last slide, Adán Cabello recently has been saying, there are no laws. Anything that is allowed must happen. Have any of you heard Adán speaking this way?
This was as if he were in front of us now.
Well, I just wonder if you could elaborate a little bit on how this compares or contrasts with whatever Adán Cabello is saying.
I mean, certainly I wouldn't say everything that can happen must happen.
Adán does that.
Yeah, no, sorry. I wouldn't say that.
I'm looking at the person who's...
Well, Adán says a lot of things, so...
The message of freedom here is not that everything must happen or so, or but it's that well, I mean, our formalism does not constrain the world. A quantum system is basically free to react to me as any way it chooses.
In the same way as when I make a probability 1 assignment to albatross winning. So in your previous example of the horse race. So the probability 1 assignment doesn't compel the horse to win.
It certainly doesn't.
And that's all you mean here? That's what you mean here?
That's what I mean.
Okay.
So you wouldn't say that it constrains the world, but you would say the Born rule is still something about the world, though, right?
Yes, it's a structural property of the world, yes. So here's my quote. Wenn schon, denn schon, in for a penny, in for a pound, in this nice translation. I still do not believe that the Lord God plays dice. If he had wanted to do this, then he would have done it quite thoroughly and not stopped with a plan for his gambling. In for a penny, in for a pound. Then we wouldn't have to search for laws at all. So this is a letter by Einstein to Fritz Reiche and his wife from 1942. Basically, QBism says, well, yes, we shouldn't have to search for laws. There are no laws in this sense. The quantum formalism actually is a different kind of law. It's not a law that tells the world what frequencies to generate for certain experiments or so. It's just a law that tells us how we should organize our gambling commitments. Okay, so this is, I mean, something that John was mentioned. So what does QBism say about the world? It makes strong ontological claims.
I think you have a question.
Yes?
If you're talking about gambling commitments and you say that your formalism leads you to a situation where you will always lose if you apply it in a certain way, would you then say you should revise your formalism?
It would, yes.
Okay.
It would.
Good.
This is, for instance, how you can derive, or how you do derive the classical formalism of classical probability theory. So you can derive it from the requirement that you shouldn't predict a sure loss. So here are my ontological claims. The first is the world is bettable. So the world actually is such that it allows for a structural property like the Born rule. This gives you a form of structural realism. Another ontological claim is that measurement outcomes are personal to agents. No laws that constrain how systems behave, as I just mentioned. And that leads to the fact that the world is capable of genuine novelty. So these are what I say, but the ontological commitments or claims of QBism.
What does genuine novelty mean? Again, to contrast against Adam, who would say the world is random. Is that what you mean?
Are you a
I'm obsessed with Adam.
I should have invited Adam.
Why don't you comment?
Well, it's just not clear that if you haven't been reading William James for the last 15 years.
Only 15, Chris?
It's been more than that.
It's been more than that.
Yeah.
Oh, there's the gray hair thing again. That you might not know how that notion has a different nuance than Adam running all over the world.
Why don't you ask Chris? Why don't you ask Chris in the lunch break of how different the nuances are between this and
I think I have an idea of what might be the difference, but I don't want to speak for Adan because in the end his view is. But I think from what I understand from what he says, his idea is that the world is as random as it can be, while still obeying whatever minimal properties are necessary for us to talk about it as a world. And so the idea is to take randomness as a kind of principle for deriving the laws that govern the world. But once such laws have been so derived, they must be that way for now and for eternity. Whereas the QBist would say, well, the world seems to be orderly based on the evidence of my senses, but I have no justifiable belief that it should always be that way, that at any moment it could simply stop being orderly. At least this is my understanding of the difference.
Well, the Born rule actually gives me very good reasons for betting on the world continuing to be orderly. So I don't agree with that. In my gambling behavior, I will. The fact that I have a formalism here that allows me to gamble and actually quite successfully and build machines actually, makes me predict that the predictions are just those of order and predictable results. So.
Why is not a law natural law then?
Sorry?
Why the Born rule is not a natural law in this?
A law.
Why? Why don't you call it a law?
Well, I call it a law. I call it a law that it's a normative requirement on my gambling commitment. So you could call it a law of that my gambling commitments have to obey. Yeah, yes, but if you think about the law of nature, very often you think of a law that constrains the way that systems behave, and that is a different idea.
How about the Rudiger equation?
Well,
it doesn't exist, or it's not a law, or
It's a special case of the Born.
It exists, but it is actually in the same vein here. It's a law that restricts my gambling, my gambling behavior. So it has the same. It has the same state.
Would it help to mention George Boole, who called probability theory a law of thought?
If you like.
So a law of thought versus a law of nature.
So yeah, but that is actually.
And then the Schrodinger equation would be a law of thought.
Well, the Schrodinger equation would have the same status as the Born rule on this, yes.
Could I go back to an earlier answer you gave? So, as you pointed out, the assumption that there is no money pump is used to derive classical probabilities. So, do you have some analog, something like the assumption that there is no D money pump that is used in your theory to derive the formula for total probability, but with the D parameter in it?
That would be very nice to have something like that, but we don't have it at the moment. So, I mean, it is actually a project to derive the Born rule from considerations like that. In the end, though, the Born rule is, like the Schrodinger equation, an empirical law.
As is probability classical.
I wouldn't say that, no. Probability classical is purely normative. You can derive it from the idea that that if we regard probabilities that lead you tell you an action that leads to a sure loss is rational, well, that's so. If you want to rule that out, then you get probability theory. So there's no empirical element there. Whereas the Born rule and the Schrödinger equation are empirical. So I think there's an important difference here.
But you would be interested in a normative derivation.
I would be interested in that discussion, definitely. Yes.
Okay.
Yes.
I don't know if I keep going with the discussion now, but again on the relation between the Born rule and some notion of realism. So I think one of the minimal assumptions of realism is to explain the regularities in the world. How can the Born rule describe those if I can, decide differently for what the Born rule suggests me to do?
Well, I disagree with I wouldn't say the role of physics is necessary to describe or explain the regularities in the world. In some sense, the Born rule as a gambling formalism can do that. Actually, it doesn't explain in the usual sense, but what it does, it makes me expect the regularities. So in that sense, it is an explanation. If you say the world, this is a property of the world, and if I apply the formalism, I say, well, I expect certain regularities with probability very close to 1. Well, I mean, that's probably as good an explanation as you're going to get.
But at the same time, nature doesn't have to live up to your expectations.
Yeah, so my question is about the relation with the realism.
That's very true. I say, no, it doesn't have to do that. And very often it doesn't, and sometimes it doesn't. That's very true.
More often that.
Okay, yeah, sorry, I'd like
It might
to
be
move
too
on.
much to add, but you align cubism with structural realism, whereas structural realism is what replaced observers observe in Matt's talk. So I just don't know what structural realism means.
I second that.
I don't think anybody knows.
Okay, let's maybe postpone that. It's a nod to structural realism. It's not. Don't say that cubism is structural realism, but it certainly has some affinity there. So, what are agents? Here's sort of a tentative definition. An agent is an entity that can take actions freely on parts of the world external to itself, and can experience the consequences of these actions. So that's a very, very wide and general definition. Also, you will see it does not make any mention of quantum mechanics, so agents in this sense clearly existed before quantum mechanics existed. I mean, many people would always count as an agent in this definition. Now, if you add quantum mechanics, you get a user of quantum mechanics. So as a user of quantum mechanics, I would say is an agent that's capable of applying the quantum formalism normatively. So that's sort of it's a working definition, but that's roughly what I mean when I say agent. And this means, in particular, that a team of scientists sharing notebooks, calculations, observations, etc., can act as a user of quantum mechanics, and thus is a single agent. Now I'll come to a little thought experiment here. This is about the coffee queue. So I propose a gamble to Chris. You're both waiting in the coffee queue. I propose a gamble on what choice the next person in the queue, let's call that person A, will make. If A chooses black coffee, I pay Chris $2. If A takes milk, Chris pays me $1. Chris agrees. We both think that's reasonable, and so we do this lots of times. There's a long queue. Probably in the end, Chris is going to be ahead a little. It's a bit like Rosenkranz and Guildenstern are dead. You just basically each time you flip and you exchange money. Now finally, it's my turn in the queue, and I'm the next to take coffee. Okay, so it's my turn to choose black or white. So I propose that so the gamble becomes this now. If I choose black coffee, I pay Chris $2. If I take milk, Chris pays me $1. Chris says, no, I'm not going to play this. I say, why not? Is it maybe the probabilities? Let's change it. No, he's still not playing it, so I don't know why. Well, it's obvious why, right? It just doesn't make sense. It makes no sense to gamble on yourself. So it does not make sense to assign probabilities to yourself, and does not make sense to assign a quantum state to yourself in this context.
Except we do every day.
You do?
Sure. I mean, when we, when we, so if I apply for a bunch of jobs, for instance, right, I may have to make a gamble on what I may choose to, let's say I get 5 or 6 offers, what I may choose down the line. I may have to make some kind of a gamble on that.
Oh, but I think this is really different. I think this is an ordinary gamble on the world. You will have to make a decision, so you constantly have to make decisions based on uncertainties. But you make the decision, and the world responds in a way that you can't predict. So I think this is the kind of gamble that you would have here, where you make a decision on, in this case, whether to accept this gamble or not, or to go to take these odds or these odds, or apply for this job or that job, or to take that job offer or that job offer, because you don't know what the world is going to throw at you afterwards. So it's not.
Or maybe you don't know what you're going to do afterwards.
But in this case, he asks dumb Chris, can you go to that slide? To the dumb Chris slide. Finally, it's my turn next.
No, it's not dumb at all.
I think he wants the $2,000 one.
Yeah. So maybe I disagree with his odds, so I say, okay, now I accept it. And the moment that I accept the gamble, he just changes which strategy he's going to use. He chooses the opposite kind of... Do I misunderstand?
No, I can. I mean, because I can't gamble on myself, because I can make any outcome happen.
It's not that you can't gamble. It would be stupid for me to accept your gamble.
It just doesn't make sense for me to even propose a gamble like that, because I'd say it's just internally inconsistent and contradictory to gamble on yourself.
If you were a shyster, you would. You would propose a gamble like this to see if I'm a sucker.
Okay, but that would.
And then if I accept it, I'm the sucker and you win. But the point is, you can make yourself win. Whereas when you perform a quantum measurement, you cannot make yourself win necessarily.
In decision theory, this is called Newton's paradox. You get a formal contradiction between expected utility, maximization, and dominance. But you can resolve it by distinguishing between your current and future self, which is, I think, what you're describing. And in that case, you would escape the paradox. But I think here you're not really getting into that kind of level of detail.
But I still maintain, and it does not make sense to assign probabilities to yourself. If you can choose the outcome, which similarly, it does not make sense to assign.
Well, that's the crucial sentence. If you can choose the outcomes.
But there's always the assumption that you are actually free. You're a free agent.
I'm assuming here that when you talk about yourself, you mean something more than just the physical aspects of yourself. Like surgeons can do surgery on themselves and presumably can assign probabilities to themselves having heart failure or something.
I mean, basically, what if I take action on a part of myself, my hand or so, right? When the criterion is that what remains, sort of, this side is still an agent, and I gave a definition of that. So what remains must I can basically then treat my hand as something external from myself in this way.
So it's a kind of classical or non-quantum version of what Matt called Heisenberg cut.
I have some examples of neurosurgery that I want to talk to you about in the break.
I just want to put this in context of the Wigner's friend experiment. But what I want to say is that, I mean, I agree you cannot gamble on yourself, but the situation of Wigner's friend is rather like gambling on some other agent's belief about yourself. So in that sense, Wigner's friend can think what kind of a state Wigner assigned to the friend.
Well, I can
This
do
is-
this,
and
but
I know. I mean, at
that's
least at
fine,
the
that's
APS
fine.
meeting, you wanted
Because
to avoid.
how do I do this? If I gamble on, if I ask myself, well, what state is Wigner going to sign? Well, I can say Wigner is going to sign that state, and how do I check that? By asking Wigner. So that's fine. I think there's no problem, because you're talking about you're now talking about something that Wigner might tell you, and you can certainly do that. Okay, so let me just briefly mention QBism versus Copenhagen here. I mentioned already that I thought that QBism wasn't Copenhagen. I think Copenhagen interpretations, maybe not all of them, but I mean, for instance, certainly Landau and Lifshitz would say that a measurement outcome is an objective feature of the world. And QBism, as I've said several times, does not subscribe to that. And that has consequences for Wigner's friend. So my standard approach to Wigner's friend would have been like this. Well, the friend makes a measurement in a closed lab, gets an outcome. Wigner is outside, doesn't experience an outcome, and was in an entangled state. Right? That's in a nutshell the experiment. Now you get a paradox if you assume the measurement outcome is an objective feature of the world, and either the friend is hallucinating or Wigner is inconsistent, or I mean, of course, you came up with various ways of trying to sort this out, but this is really, in a nutshell, the problem. And if in QBism, the paradox simply does not arise because the friend's measurement outcomes are personal to the friend. But the recent sort of kind of ingenious twists and variants of Wigner's friend sort of makes for somewhat more interesting answers. And so let's just look at these two, Daniela Frauchiger and Renato Renner, and Veronika Baumann and Czesław Bruckner. They're very different papers, but there is a common claim here. The claim is, or the idea is, that Wigner and the friend, they can come to contradictory conclusions about the same potential outcome. So in the Baumann and Bruckner example, it is predictions about the measurement that Wigner will take. So both friend and Wigner have take a view on that. And in the Frauchiger and Renner case, it's well, one of the friends and Wigner who make different contradictory predictions about a particular outcome, again of a measurement that Wigner is making. So it's similar in this respect. And the QBism has a categorical reply to that. Two agents cannot experience one thing. So basically, these two teams might think they have come up with an example of that, but they really haven't. It's still true that Wigner and the friend are talking about different things in both cases.
To make a point, I mean, when you say that, that does involve the eigenvalue eigenlink assumption, because if you, I mean, it involves the assumption that, you know, if you get a certain result, then the state's an eigenstate.
So we're going to say what? Sorry.
Where the Wigner is saying contradictory conclusions. I mean, the conclusions are only contradictory if you suppose, for example, that the friend has made a measurement, so now the friend is in an eigenstate, but Wigner has, you know, an entangled state, and that's contradictory. But, I mean, but it's only contradictory with respect to what they see if you're assuming that because the friend sees something, that contradicts the fact that the outside state is an entangled state. I mean, you're assuming the eigenvalue-eigenstate link there.
I'm not actually even endorsing this. I'm just saying that these two teams are trying to make constructions that lead where they come to this contradictory conclusion. I'm going to criticize it. So
I have to correct you, because the aim of this paper with Veronika was actually that the friend himself alone comes to the conclusion that the fact that if he or she takes only the facts in the lab, this is in contradiction with what she will see later on. So it's really avoiding two agents. That's the whole.
Okay, no, I think I disagree, because in the end, the friend is going to make a statement about a measurement that Wigner is performing.
This is formally there, but at the end there will be just two lists that friend can inspect alone and convince her.
But by drawing up the list, you're basically hiding the fact that the lists are things that are about measurement outcomes, measurements that Wigner has performed. So
this is for you unimportant. You said you just want one agent, and what I want to say is that's an example where you have one agent getting convinced.
So this is really what you're doing, right? So in your protocol, after the friend has made the measurement in the lab, Wigner performs the measurement on the joint lab-friend system.
Is Wigner here conceived of as another agent?
Wigner could even be a machine. It doesn't matter. But it's fine. It's
according to my definition of agent, that might actually work. I mean, as long as the machine is able to apply quantum mechanics.
It's not the end of the problem.
Well, I think what Jacques is trying to get at is that the friend could construct Wigner. Wigner is a device.
Well, certainly you could come up all kinds of further. You could come up all kinds of further twists on this. But let's tell me my story, and then we move to further. Okay. So, what prediction should the friend make about Wigner's outcome? That's the question you're asking, and you're saying that the friend can actually get. Well, I mean, the problem is the friend, depending on what reasoning the friend uses, comes to contradictory conclusions. Okay, and but what I'm saying is that quantum mechanics is of no use to the friend here, because it would require the friend to assign a quantum state to herself.
So you say you should never gamble.
No, I'm not saying that. Basically, gambling was invented by the Romans. This was long before quantum mechanics. Actually, this is not a joke. This is a serious comment. I mean, there's lots of other bases for making coherent and sensible decisions, even if you don't base them on quantum mechanics. So
what is the conclusion of the fact that the agent then that the friend realizes that the prediction based on the facts in the lab were wrong? What would be the lesson from quantum Bayesianism?
Just repeat what I said. The friend in this situation is considering a measurement on himself. So, and I would say that quantum mechanics is not equipped for that. So you cannot assign a quantum state to yourself. So therefore,
but operationally, he can convince herself that it was a wrong prediction, based on the
trying to do that.
What is the wrong prediction? I'm saying that the agent is not quantum mechanics is not able to give the agent the friend a prediction, because that would require the friend to assign a quantum state to himself. So therefore, there is no wrong prediction the friend will ever encounter. That's as simple as that. The friend could of course still make a prediction. But that would be very similar to the prediction I make if I undergo surgery, right? I mean, I trust the anesthetist surgeon team, even basically based on their experience and their track record, etc., that when I wake up from the surgery, in the end I will be fixed. So that is a prediction and a decision I make not based on quantum mechanics, and that's perfectly rational. But quantum mechanics has nothing to do with it. Same here. Since the friend cannot use quantum mechanics because it would mean assigning quantum state to himself, which is contradictory, the friend will have to, might. If the friend wants to make a prediction, then this is one rational rule.
Just last comment, and I will not, and we can discuss later on, but the fact is that if the friend uses the wave function as Wigner assigned to the friend, she will make good prediction. It will matches with the observation later on. And you say she's not entitled to do that, although it matches the predictions.
That we don't have a theory that allows consistently. So basically, if you want to make that move, I think you should be required to come up with a consistent theory of what it means to assign a quantum state to yourself, not just in a particular thought experiment, but more in general. So that would be my answer here.
Wouldn't that suggest that quantum mechanics is either incomplete or not universal?
Neither. It's complete in the sense that I can use it for making decisions and gambles on any action I take on the world outside myself.
would only be incomplete if you think of it as descriptive, right?
Let's move on to Fachanwendung, because I think I shouldn't. We should go to lunch eventually. So here we have 4 players: Wigner, an assistant, and 2 friends. So let's call one of our friends Alice. At the end of the protocol, Wigner performs a measurement. And at some earlier stage, Alice makes a prediction about Wigner's outcome. It's a private prediction because she doesn't communicate it to anybody. So Wigner's predictions and Alice's are contradictory. But the standard QBist answer still applies. 2 agents cannot experience one thing. Alice's prediction is about the consequences for herself if she performed the measurement, and Wigner's is about his measurement outcome. They're just not the same thing, and there is no requirement of consistency here. But let's dig down a little more on this. So there's no conflict. So it says this: well, let A and B be 2 agents who start with the same prior knowledge about the experiment. Or I'll piece it together. So this is. Let me just say. So there is this key condition C, which they correctly identify as not compatible with QBism, and I would like to dig down into this slightly, because it is incompatible with QBism on several levels, and I will then end with the key. Maybe the key thing here. Let's talk about prior knowledge first. So the starting point for the condition is that A and B are 2 agents who start with the same prior knowledge about the experiment. Now, what I said about QBism being not a theory that just moves from initial conditions to final conditions, but is a theory that is a consistency criterion that doesn't put any of these things prior. It also implies that 2 agents never actually have the same prior knowledge. So this very starting point is already denied by QBism. There is now a step. So given these assumptions, the agent A has this particular belief. The agent says, I'm certain that if I checked B's notebook at some particular time, I would read that B is certain that statement S holds. Now, it's a fine statement, but one should be very careful here and not draw wrong conclusions, because unperformed measurements have no results, even in the case of certainty. So even if I have this particular certainty here, I'm not allowed to just conclude that this means that the statement actually holds. In order to make sure it really, that this sentence is in the notebook, and to make sure that this is the case, I would have to perform the measurement. And actually, of course, in this case, the whole experiment is set up in such a way that making the measurement actually does make a difference. So it's not the same thing. An unperformed measurement has no results, even in the case of certainty. Yes?
Well, no expert on F&R. I read that statement to be one agent's beliefs concerning another agent's beliefs, which I would imagine is a kind of statement that QBism, being very Bayesian in its nature, would certainly want to allow. So where am I going wrong in relation to what you've written in your slides?
Because you're wrong that QBism would allow statements about a different agent's beliefs. QBism in the quantum mechanics makes statements about my expectations for the consequences of my actions. So I can make a statement of, and this formulation of the condition is actually already a nod to QBism. It's from an email from Renato to myself where we were trying to come up with a version of the condition that is compatible with QBism as much as possible. So you can make a prediction about. Let's say I ask you, what's your belief? And I can have views about what your answer will be. But if I reason directly of what your belief is, I would be reasoning about hidden variables. So that would be outside of what QBism would do. And this is why we have this formulation here. We are asking about if I checked the notebook. So actually, if I made a measurement, I would expect to find this particular outcome. But I'm still saying if I don't check it, I have no right to assume that that unperformed measurement actually has the result that I expect. So then comes the rest. Actually, it's all there. It's just not never in its entirety. So the assumption C says it allows agent A to transform any statement of the form I'm certain. If I check B's notebook at some time, I would read that he or she is certain that statement S holds, into direct certainty that the statement S holds. So that's the key thing here. And basically, QBism says there is no requirement that I have to accept another agent's conclusions or judgments. So that's just basically not a requirement of quantum mechanics. And of course, I mean, Rudiger and Wigner know that because it's a separate requirement from from quantum mechanics. So now let's on to my last slide. So doesn't this put an impossible burden on coming to agreement, on scientists working together, on making basically, I mean, having any proper normal communication? And the answer is no. It just puts a nearly impossible burden on applying quantum mechanics to friends or agents, and that we know, of course. But remember, a team of scientists sharing notebooks, calculations, observations, etc., can act as a single agent. So if you have a team of people working together, PhD students, people doing the experiments, reading out, I mean, they can perfectly easily share their notebooks, calculations, observations. They act as a single entity, a single agent, make predictions, experience the consequences. So that is just like the scientific community works. Now, can the four agents of Rudiger and Wigner's thought experiment, Wigner, assistant, and two friends, can they be thought of acting as a single agent? And then the answer is clearly no, because that would require them to assign a quantum state to themselves. Or at least this entity, agent made up of four people, would have to assign a quantum state to itself, which I would like to rule out. Thank you for your attention.
Any questions?
So for your last slide. So the whole scientific community, all humans on Earth are a single agent in this sense. You're saying. So what's the point of having QBism with different?
I'm not saying that.
I said that how the scientific community works. They share the same data. They have public access to the same publications of the.
That will work. The scientific community, in that sense, yes.
Yeah. So having the access to scientific journals makes us a single agent.
You have to share the same preferences. You have to share the same utilities as well, and not all scientists do share the same utilities.
They should be able to agree on bets, which is not realistically true for the entire scientific community.
I think the more fundamental point is that, the way Chris and I put it, is that quantum theory is a hero's handbook for navigating the world, for managing one's expectations as one gets confronted with and tries to interact and navigate the natural world. And that handbook is very neutral. It says very little about the character of the user of the manual. And it doesn't say anything about the memory capacity or energy use rate in kilojoules or anything like that of the agent who is using the manual, who has picked up the handbook and adopted quantum theory as an expectation management tool. So it is in principle possible that something from the outside which looks like an entire scientific community could be acting as a single, could have collectively picked up that entire handbook, and used it to manage expectations, simply because nothing in the formalism of quantum theory rules it out. Whether that's actually the case is, I think that there's enough disagreement within the physics community that you probably shouldn't think of the entire community as a superorganism of that sort. The real point is that quantum theory doesn't say enough about the character of the agent using the theory to rule out that scenario.
Well, if you appeal to the fact that there is a disagreement within the community, then none is right and none is wrong, right? Everybody is entitled to. You said that we cannot consider them as a single agent because they are just not agreeing.
Well, I mean, I think Reinhardt's point was exactly to the point. I mean, there might be examples. For instance, let's say we found an asteroid that hurtles towards Earth, right? I mean, then we might actually have a very large set of people who are just have the single aim trying to divert that thing, and then you could really think of them, large fraction of the scientific community acting as one agent. Yes, but it has also to do with the decisions you want to make, your utility functions, and your aims and. I mean, a good example from probability theory is husband and wife sharing the same bank account. So, I mean, normally in probability theory, there's no requirement on different agents having the same probabilities, right? There's just none. The decision theoretic axioms, they refer to a single agent. But if you have husband and wife, they share a bank account, well, then it's very easy to Dutch book them, to just basically fleece them if they have incompatible probabilities, because they make decisions that will lead to a sure loss to the bank account. So they better had to act as a single agent, and so that's an example of how this works.
It's this question.
Sorry, that's not
go ahead.
Chair, yes, sorry.
So just, I don't know if your question was. Okay. So just again on the relation between QBism and realism. So is it right if I say that according to QBism, quantum theory does not provide a full description of the reality outside, just provide a description of this normative rule. But there is something else that quantum theory can. For example, you talk about external world, you talk about an asteroid coming, and so on. And so QBism says that quantum theory doesn't tell anything about that reality.
Well, nothing and everything. It tells you everything about how to act on this and what consequences to expect. So in that sense, it tells you everything about that part of the world. Yes, but it does not give you a description. There is no mapping between the objects of the theory and the world. It just tells you that in that world, this is a rule that tells me how to act.
But you still believe that there is an external world.
Oh yeah, I mean, that's the very first starting point. When I say an agent is an agent.
But quantum theory just tells you how you should bet on this world, not about the world.
Yeah, just because there's quantum theory doesn't mean there have to be asteroids in the universe.
But I just want to inject here that presumably this is a perspectival world. So when we talk about reality in the context of QBism, it can only mean the reality for that agent. That if you want to consider many agents, you have to consider many realities in that sense. Many asteroids, as it were. At least that was my understanding of the extent to which you can talk about reality in QBism. It has to be a plurality.
Yeah. So on this, may I say just what I thought before this talk? I thought that you had in mind some, let's say, an ontological framework for participatory realism, which is, different from, for example, hidden variables, in the sense that you always assume that there is a reality, but that must be a function of an observer. And so you might think that if you put together the function of all the observers, then you might say, oh, this is the world. Okay, just maybe I'm not seeing that part of the world, but I'm not saying it doesn't exist because there is another observer look at it. And I thought you were thinking more in these terms, because otherwise, if you don't say that, then you have to conclude that you cannot talk about external. I mean, the quantum theory doesn't tell you anything about the external world.
I mean, that's a different project you're describing here, but I certainly disagree, and I'm not going to repeat the argument. I disagree with the fact that I'm not saying anything about the world. I'm saying everything about the world in some sense, just as well.
I disagree. I disagree. Okay. I find the following analogy helpful. Let's see if you find it helpful. In 1689, what year did Newton find his law of universal gravitation?
Whatever year. That year.
16-something. Newton posited that every two bodies in the universe attract each other with a force that was proportional to the product of the masses and inversely proportional to the distance between them squared.
Well remembered.
You remember?
Well remembered.
Well remembered. So Newton posited this universal theory of gravitation. He wrote the Principia. With the Principia and his discovery of calculus, he was able to solve an immense number of astronomical problems. He was able to explain tides. He did a lot with that theory. Did that theory, law of universal gravitation, did it tell us to expect that plants absorb sunlight by chlorophyll? No, it didn't. Did the theory explain various other kinds of chemical reactions? No, it doesn't. Did the theory explain how the sun shines, why it shines? It doesn't do that. What the theory does is identify one salient and important property of everything in the world. To that extent, Newton's theory of just one thing, not Newton's theory of everything, Newton's theory of just one thing tells us an immense amount about the world. And I would say that I think the QBist perspective is that quantum theory is more of that nature, if not exactly of that nature. It identifies one aspect of the world that hadn't been accounted for before. And because of that, it's immensely useful in the same way that Newton's law of gravitation is. But it's not going to answer particular questions of why is Dr. Catani here rather than not being here? Or it's not going to tell us very detailed particular properties of the world, but it identifies one property. And that one property manifests itself through how we should better gamble about our personal experiences.
I understand. I thought the scope...
And to that extent, that's an ontological style statement. It says there's something about the world that compels this rule.
But there might be other theories about other ontological statements.
Or there might just be other things. I mean, we could take an extremely empirical stance. This is why I pushed Matt on, would you call this, one of your criteria for a Copenhagen interpretation was something to ask you, is this a broadly empirical stance? And I think that QBism, at least as I understand it, is resting on a very strong empiricism that the world is filled with lots of particular things. Quantum theory is not about the particular things, but about how best to gamble in light of some certain character of it.
Yeah, I just thought the scope was broader because it explains how the atoms behave.
So the way I disagreed with Rudiger when he said it says everything and it says nothing is, no, I think it says something very firm, but not about particulars of the world.
I mean, you can.
So it's not at all saying everything.
You can apply it to anything.
You could apply it to
any system.
Let's have Czeslav's question and then break for lunch because he's been waiting.
So I posed this question many times in the past, but this time I posed it perhaps a little bit different. So we can think about different probabilistic theories like classical quantum, but maybe even some post-quantum. We are not very successful in completing these theories, but there are some candidates when you think about the single systems. And for this probabilistic theory, I can take a Bayesian point of view and think about normative rules, agent, and basically involve the language that you guys are using for the quantum theory. And now, what is the aspiration of QBism is that the only way how you should gamble is the normative rule are according to the normative rules of quantum theory. And if this is so, then it seems to me that it's not about gambling in itself, because you can think about gambling in many different probabilistic theories, but something else. And this something else seems to be much more interesting than only the normative rules of the gambling. And this is, I acknowledge that a lot has been done in reconstructing quantum theory from Bayesian rule. But then it seems to me that the most important ingredients for reconstructing will not be about gambling alone, because I can have gambling in many different probabilistic theories, all of them empirically different.
Well, I mean, let me just first of all say that I would never put classical probability theory and quantum mechanics sort of as competing or as alternative theories. I even put it somewhere on my slides that the quantum formalism here is an addition to classical probability theory.
Is this the only addition?
Sorry?
Is this the only possible addition?
Not the only possible addition, but it is an actually pretty good addition, as we know. I mean, we all know that this is a very, very good theory. And well, I mean, it's empirical success. It's empirical success. I mean, the Born rule is empirical. The quantum formalism has an empirical basis, but it's certainly not one replacing the other at all. So it's there are situations. So I apply the Born rule or the quantum formalism only if I actually have. If I assign quantum states, if I have reasons to assign quantum states, if I'm actually in a situation where I would do that. So I mean, I haven't used quantum mechanics. I don't know if I've ever used quantum mechanics actually to make any decisions, because I mean, the only physics experiments I've ever done were sort of lab experiments where I just followed the instructions in the handbook for. So quantum mechanics doesn't replace that. It actually is. There are rules that apply when I have these additional beliefs, these very specific beliefs that can be translated into quantum states. So in that sense, it's really not at all replacing classical probability theory. It's not one or the other. Or they are not just two different ways of looking at the world.
But using Hilbert space and the probabilistic structure of Hilbert space that we're used to is a statement about the world as well. You said it's an empirical thing, right? So this is what you wanted to hear, right? So it's not just some normative thing that somebody came up off the top of his head.
Absolutely not. No.
Yes. Okay.
The fact that we can do that is a very profound statement about the world. That's more structural.
I think a bit more what's particular about these cases in which it's appropriate to use the QBist version of the Born rule is that it's a situation in which the fact of making a measurement matters. So where what's relevant to your betting is whether or not you actually did a measurement. And you will have different beliefs about your bets depending on whether the measurement was actually performed or is just one that you could have performed but didn't.
Isn't this just basically a more elaborate version of saying unperformed measurements have no results?
Yeah, but I think the Born rule is telling us how our beliefs about an unperformed measurement constrain our beliefs about the actually performed one. And this is an empirical thing because it just so happens that in some particular circumstances this is the case, that there is this set of constraints between.
I agree with that.
In fact, that's the way I would say Born rule should be understood. It's that how we would gamble on some experiment that we could do informs how we should gamble on one that we're actually going to do. But and the constraint is a non-trivial one that we wouldn't have foreseen before quantum theory.
One that we learned empirically.
One that we learned empirically.
Why you deny the descriptive part then, if this is based on empiricism?
Oh, it's descriptive of our belief.
Yes, descriptive about the rule, but the quantum states I wouldn't say are descriptive. So the terms that go into the relation are not descriptive. But the relation, the overall rule, is descriptive.
I think we should probably close the discussion now and thank Rudiger again for his talk.